Hello everyone and welcome. Today, I'd like to talk about lowest common ancestor of a binary search tree. So you have a binary search tree here and you are given two nodes, P and Q. You are asked to return their LCA, which is 6 here. You may be noticing there's a similar question called lowest common ancestor of a binary tree. If you're interested, please feel free to look up this other video in my channel, which has a time complexity O(n) and a space complexity O(n) as well. But by leveraging the property of a binary search tree, we can improve this complexity matrix. So how can we do that? Here are two key observations that can help us to find the LCA in BST. First, due to the binary search property behind BST, the node's value of the LCA, which is 11 here, must be somewhere between the P's value and the Q's value inclusive. So it must be between 3 and 18 inclusive. Second, when traversing from the loop node, which is 19 here, as soon as condition 1 is met, it's guaranteed that LCA is found. This is because it takes two unique passes from the loop node to reach to P and Q. So this unique path to reach to P and the other unique path to reach to Q. And these two passes meet only at one node, the LCA, but not any node below the LCA. In fact, if you look at this tree structure, if you split at LCA, the left subtree no longer reach to Q, and the right subtree no longer reach to P. Here's an example to illustrate the idea that it takes two unique paths from the loop node to reach to P and Q. So from the loop node T, you have TRACE reach to the word trace, and TRAIN reach to the word train. And these two unique paths only meet at the LCA, the letter A here, but not any other node below LCA. With all the background introduced, now let's write the code. So first of all, we want to make sure the P's value is less than or equal to Q. Otherwise, we swap them. Second, we will do a while loop. If the loose value is less than P's value, then we move it to the right. Move toward the range of P and Q. Else, if the loose value is greater than Q's value, we move it to the left. Again, the goal is to move toward the range of P and Q. And finally, if it's between or somewhere in between that range inclusive, then we have found our LCA. So simply return root in this case. Okay, so that's all it takes to solve this question. And let's submit and see how it goes. We submit and it's done. 56 milliseconds. Pretty good. So finally, we'll analyze the code for complexity. So it has a time complexity of OH, where the H is the height of the tree due to the binary search property. Second, for the space complexity is O1, since we don't, due to not using any stack for recursion, instead we just use those constant space variable here. All right, so That's all for this code and for this question. Hope you find this video to be useful, and please subscribe. Stay tuned for more videos. Hope to see you next time, and goodbye.